Hi, we are from Group 4 and this is our questions. So I will be explaining the question given to us, Group 4. So for the first question is a cross-section of long cylindrical structure with hollow core is shown in figure Q2A. A radial section of B minus A mm thickness is filled with volume charge of rho V say coulomb over meter cube. Find the expression of electric field intensity within regions R less than A and R between A and B. Then determine the electric field intensity at the given point. Note that Z in is an arbitrary point on the z-axis. So at first we choose R less than A region. So for the first, we need to use the Gauss law, which is that integration of E times dA equal to Q enclosed over epsilon naught. So we mark it as the first equation. So because there's no charge inside the region of R less than A, means that Q enclosed is equal to 0. So we substitute the Q enclosed equal to 0 into the first equation. And this is the new equation. So because of that, we got the electric field equal to 0. So thus, we could conclude that electric field in region R less than A equal to 0. So for the next part is when R is in the region where it is greater than A, less than B. So the charge density in this region is rho V. So the formula of rho V is Q over V. So for the cylindrical structure given here, the volume is pi h times r square minus a square. So we can also find the charge enclosed with the formula is Q equal to rho V times V. So which then become rho V pi h times r square minus a square. And then we substitute, we use the Gauss law that I said in the first question. We substitute this Q, this new Q we get here, into the first equation. So, and then for the A, so this one E dot A dot dA, the A we make it into 2 pi r h. So then the equation is become E dot 2 pi r h equal to rho V pi h r square minus a square over epsilon naught. So then the electric field is then become rho V times r square minus a square over 2r epsilon naught. Therefore, the electric field in region R greater than A less than B is rho V times r square minus a square over 2r epsilon naught. So for the last question, which is determine the electric field intensity at A over 2, and Z. So for this question, the electric field in region A over 2, Z lies in region R over A, which is this one. Which means the electric field in this region is 0. So the answer for this question is that the electric field region A over 2, and Z is 0.
The second part of the question, consider a new design of hollow core cylinder with center of the core is now shifted to coordinate A0Z, such as shown in figure Q2b, By applying the Gauss law and superposition principle, find the resultant electric field intensity at the given coordinate. Note that Z is an arbitrary point of the Z-axis. So the hint to answer this question is the sentence by applying the Gauss law and superposition principle. So we can get the resultant electric field intensity at the coordinate. So by looking at the design consists of two charged sphere with density rho and minus rho. So we can kind of imagine the design to become two separate parts with two separate charges. The first one, the electric density due to sphere with charge density rho. So we know that electric density or E is equal to K times Q times R over R cubed. We also know that rho is equal to Q over V. So in order to find the Q, we can move the V to the other side. Then we get Q is equal to rho times 4 over 3 pi R cubed. With this cube, we can substitute it into the previous formula. So we get E is equal to K times rho times 4 over 3 pi R cubed times R over R cubed. We see that we can cancel out this R cubed. And we also know that K is equal to 1 over 4 pi epsilon. We can substitute that as well. So we get E is equal to rho times 4 over 3 pi times R over 4 pi epsilon. We can cancel out this 4 pi with this 4 pi so that we get E is equal to rho times R over 3 epsilon. So this is the electric density for the first charge. For the second charge, since the only difference is the rho, which is minus rho, we can get the electric density. The E2 is equal to minus rho times R2 over 3 epsilon. For the first one, the R is coordinate 0, 0, Z, which is in the middle here. And the second part is A0Z, which is in the middle of the second charge. So after having the E1 and E2, we need to apply the principle of superposition in order to get the E. So E is equal to E1 plus E2. So we can get rho over 3 epsilon with R1 minus R2. So by the end of the answer, we get E is equal to rho A over 3 epsilon.